All right, welcome back to Communicating Computer Science. Today I want to give a little primer on what empirical science looks like and a qualitative statement of what statistics is used for. We won't dig very deep into that, but I think to the extent that you want to be able to read papers from empirical science in humanities, I hope that this helps a bit. Some of it may have been covered in school for some of you, but my experience from the past was not so much actually for most. So I'll ask you afterwards how much of this was new. So we have the scientific method as how do we learn things when there's no definitive truth. A little bit of statistics, and then coming back to the pre-session task about what could potentially go wrong. The goals are give you some vocabulary, specifically at the end for papers in our context, computer science education or education research in general. Yeah, I think that might be useful. Have some intuition about what statistical tools are used for and how they can be abused. And yeah, leading into spotting these pitfalls, hopefully. Now, we'll do this at a very basic level, but the reason why I'm doing it at all is that you haven't probably seen it, at least in university. Computer science is not a natural science. It's a bit weird what it is, actually. Is it a structural science, more like mathematics or theoretical physics, where we live in an abstract world that we construct ourselves and we just prove theorems in this abstract world? For some part of computer science, that's definitely true. The part that I teach in my other class, for example, basically lives detached from reality for a long time and then only touches back in some parts. But of course, it's also an engineering discipline. And so it's one of these, if you want, you could make an argument that maybe physics was like this before, and then it's split into several fields. And now you have mechanical engineering and electrical engineering, X engineering, which is no longer counted as part of physics. And what's left in physics is more of the pure science that looks for understanding, and maybe also this structural bit in the theoretical branch of it. Computer science hasn't split. We have all of that still under our umbrella. What that usually means is that the curriculum at uni is quite full, and there's no wiggle room for any things that are not necessarily needed. And the scientific method is one of these things that are deemed to be not necessarily needed, even though in some parts, even in computer science, I think it would be quite useful. The key difference often is in computer science, it's comparatively cheap to get data. If you compare that to a psychology experiment where you have to recruit people, you have to go through an ethics committee to get your experiment allowed in the first place, then you have to run it, you have to pay people, you have to debrief them, and it's a lot of effort before you even get started. And you won't do this with 100,000 people normally. No way, it's too expensive. You'll do it with much smaller numbers, whereas computer science often can just run things on computers many more times. So we're a little bit spoiled in the sense that with more data, you can repair what we lack in statistical finesse, but a bit more structured methodology wouldn't hurt in some cases. Okay, some terms, specifically those that differ from how we use them day to day. And I'll have to be careful myself to not mix the two up when I'm talking about this lesson. What's a theory? If you just say that in common parlance, it's something that you think may be true, right? But you don't know. So specifically, like a crime investigation could have the theory that this is that the suspect is the murderer. That's what we often call theory. In the scientific method, that's quite different. So their theory is also something that we haven't proven, but it's much more theoretical, much more comprehensive. It's a set of ideas that hopefully explain how things work in the background. but it's really often a bit too abstract to concretely test that. All right, next one is experiment. Definitely prone to doing that as well. We say experiment if you just muck or mess around, right, without much care. So experimental things could be you just try something out randomly. That's not what a scientific experiment should be. Specifically in this scientific method, empirical science, an experiment is a very narrowly defined thing. It's a specific test specifically designed to test a claim, a hypothesis that you have. And it has to be of a specific form, otherwise it can't possibly give you the outcome you want. So that's much more narrow on the right. Yeah, statistics is another. Yeah, if we say statistics, colloquially, we just mean any sort of collection of numbers. Maybe if you do a survey, the statistics is just the average happiness of students, and you're happy with that as your statistics terminology. But in science, again, statistics is more a deeper subject, say. It's a branch of mathematics that deals with how can you design mathematical tests that tell you with quantitative, in a quantitative way, how much you can believe a certain hypothesis. We'll talk about this in much more detail. And the last one is an important one. Significant commonly is just anything that's important, but in this context of statistics, usually it's called statistically significant. And that's, again, a very, very narrow term that has to do with the p-values. We'll come back to that in more detail. I wanted to list it here. Is this at all something you've seen, the right-hand side? Okay. So what's the scientific method? This is all about not talking about mathematics or things where you can prove things deductively. You can define something, then postulate some theorem and come up with a formal proof. Then you don't need all this. For everything else, all the natural sciences, the best we have is the scientific method. And it's a cycle because it's not so clear how to ever stop. But you start with some observation in the real world, like apples falling down. So something seems to pull them down, right? So you come up with a theory. Maybe there's a thing like gravity, a force that pulls them down. Then the tricky bit is you want to operationalize how to test that theory. You want to make a concrete statement that you can test. And the trick here is you need a falsifiable hypothesis. You need something that you can prove wrong with data so that you can learn something from it. And the way to test a hypothesis is called an experiment. And usually the experiment gives you some new data, some new observations, and then that returns to the beginning, hopefully with a new observation. The annoying bit is you can't really definitively prove anything with the scientific method because it's always just one hypothesis that you refute. But that's hard. It's hard to have any definitive answers. You can only ever build up more evidence supporting your theory. But there's a few tricks how we can get a little bit more out of this. A key thing about all of science, hopefully nothing new, not everything that you can claim is a scientifically testable hypothesis. Things that evoke something that's out of our universe, in a way, by definition, can't be tested. So in this example, if you wanted to prove scientifically that there is a God, you may never find evidence, but someone can always say, yeah, but that's God's almighty, so he just hides very well, and there's no way for you to ever refute that claim. So we'll basically ignore or exclude any such statements. We say this is outside of the realm of science. There's still many important philosophical questions that we would like to get an inkling on, but not in this direct way. Sometimes you can break it down into some other questions. So if you think about God as a creator, then maybe you can ask questions about how did the universe come about, or how did life start? These are questions that relate to this, but they become scientifically testable because they restrict the question. And they take the out of this world part out of the claim. The more down-to-earth problem is it's not usually so clear-cut that things are true or false. In several ways. First of all, we usually have some theory in mind that is a simplification of what's really going on. Every physicist knows that what you put in formulas is an approximation and an oversimplification. It might still be useful for engineering, but it's not exactly the truth. So you expect that there's some deviations. More on the practical side, you can't usually measure perfectly. So what we need is not just a way to say we refute this hypothesis, but a quantitative way of doing that. To what extent does the data refute the hypothesis? And that's where statistics comes in. Let's bring this to our context. Now, flipping the units means that you haven't seen this, so just ignore what the theory here is. I'll explain that next week, I think. So an example from computer science education could be this. There's some theory that says people are motivated. Expectancy value theory is really a simple thing. It says people are motivated when two things come together. They have an expectation that they can succeed. They can reasonably expect to succeed. And they see a value in succeeding. It's something that means something to them. If you have these two things together, people are motivated. And if one or two drops to zero, that's usually a problem. The theory is as vague as this. There's no quantitative part of that because you can't easily put a number to either of these. OK, but that's a theory. Now, you can't really test this, but you could say, one implication of this could be if I give people a choice, then they have more control over the task. And so hopefully that enhances their performance because they're more motivated, because they can pick things that they care about, and they can have a better feeling for whether they succeed. All right? That's how you can come to an hypothesis. So the concrete statement here is this, that if you give people choice, they do better. Right? Now, notice that this hypothesis might well be true despite the fact that the theory could be wrong. There could be other reasons why this is true without the theory really being behind it. That's why if we confirm this hypothesis, that's evidence for the theory, but it can't definitively prove it. We usually have to narrow this down to make it possible, but that's I'll gloss over this. The tricky bit is, how do we test this if we know that all a scientific experiment can do is refute a thesis? We would like to prove the thesis, prove this hypothesis. We would like to show that this is true, not refute it. Right? So we need a trick. All right, first of all, how do you set this up so that you can isolate any other influence? And that's another tricky bit. So that's about designing experiments. If we take our hypothesis again, then the gold standard is to do a controlled experiment, which will work as follows in this easy case. You have a group of students, and what I should have highlighted here is random. You randomly assign them to two groups. One that is testing your claim by having the choice, and a control group, which should otherwise be entirely the same, ideally identical to the experimental group, but is not getting the treatment, in this case, the choice. So the experimental group writes about 1 or 2 topics, say, to keep it easy. They choose, and the control group gets randomly assigned topics. Now this, you already may see problems arising. What if all of the experimental group pick topic A because you made a mistake, topic A is much easier, then the experiment might be flawed. So there's a lot of details that are where the outcome is sensitive to the details. You should have topics. You would hopefully want that the experimental group chooses roughly both topics equal number of times. And when you assign the topics, you would try to mimic the number of topics that were picked by the other group. There's ways to kind of alleviate that a little bit, but it can be quite tough to set this up. That's what I'm getting at. Okay, both groups write the essay and you mark them, of course, without, so ideally double blind, which means can't be double blind if the people choose, right? You can mark it without looking at which group the kids are in, so that you don't influence it subconsciously. But it can't be double blind in the sense that the kids don't know which group they're in because they get to choose or not get to choose. All right. Then once you've done this experiment, you would compare the results. And now you have to quantify really what doing better means. How much better is necessary so that it's not just random noise, because kids are variable in their performance, and it's a group of people with variable quality in essay writing, say. So this is where statistics again comes in, because we need a way to control for the expected random variation. Okay, that still really hasn't shown us how to prove the hypothesis. I think that's coming up next. That's the problem I cited. We want to prove something, but we can only refute with the methodology. So the trick is we just negate what we want to prove. Okay, that's why people talk about a null hypothesis. That's the assumption that the effect you're trying to prove exists does not exist. So to make it a little easier here, it's easier to talk about has some influence versus has no influence, as opposed to has a positive influence. That just makes the statistics and the math easier. Hopefully you will be able in your analysis of the experiment to see that the influence, if it was significant, that it was positive, not negative. So it's often not such a restriction, but there are more sophisticated statistical methods that can deal with the other hypothesis. Let's keep it simple though. So let's say you weaken your hypothesis to there's some change. If you let people choose the topic, it somehow affects their mark. If you negate that, that means it doesn't affect it. And what we can formally say here is a statement about the average mark. So we always expect that some students will do better than others and others will do worse. But we have two groups and we can take the population average, the average mark in the two groups. So mu1 would be the experimental group average and mu0 would be the control group average. Then our null hypothesis is the two are the same. There could be a random noise, but really it has no effect. And so we expect the average to be the same. And we can try to collect data that makes it implausible that this null hypothesis is true, right? If we see in our experiment that the averages significantly differ, and now I'm using significant in the colloquial sense, shouldn't do it. They vastly differ. Then it's unlikely that the two groups really come from the same random distribution. You randomly assign students, so there's some built-in randomness. It's a randomized algorithm. It's unlikely that they really are unaffected if the difference is so big. But how to quantify that is statistics. Now, well, okay, in principle, one way to refute your hypothesis would be to get the true average over all people. Then you would know for sure. Then you wouldn't need statistics, but of course that's not very useful. The other option is well, sometimes you can actually do this, fair enough. Normally you can't, so you take a random sample. And in the design of your experiment, I kind of didn't say where these students come from. So that's another thing you have to pay attention to. How do you recruit the people in your experiment? If you do this with often your only option, the people you're teaching anyways, you have to put into the context. So this is what that type of school, and it's a high ability class or whatever it is. You have to give the context because that might have an influence on the validity of your hypothesis. But then within the group, you still randomly assign them to one of the two groups. So it's still a sound experiment. I have really one slide just on the mathematics behind this, just exemplary. So how can we say that the data rejects our null hypothesis with a reasonable confidence? How can we get to numbers in this? So we have our two hypotheses. Again, null hypothesis, in our case, no change in marks. The converse of that, there is some change. Then we have the observations from the control and the experimental group. I think capital X here would just be a list of marks or a set of marks that the kids achieved, or multi-set. And then we compute this mystical quantity, the p-value, which is the likelihood of seeing the outcomes we did get in our random assignment to groups, assuming that the null hypothesis is true. So you assume that the two groups really don't differ. Now you see some data, and making some assumptions how things are distributed, you can compute how likely is it to see exactly these values. And you see, so there's assumptions on distributions. That's where you have different tests. So depending on what exactly you assume about the world, what's your simplification, you have lots of different tests, and that's all these things with the cryptic names. We'll just have a look at the student t-test, but there's many others. There's a reason why natural sciences and humanities courses usually have a full term long course on statistics. If you want to apply this, you better know the assumptions of these tests and use the right one. For us, I think we're just consumers of this. Whenever we look at a paper that is published in a reputable journal, the reviewers know statistics very well, and this is one of the first things that they usually check. Are the statistical methods sound and reasonable for this application? So we can, in a way, chicken out of this and say we just take what people in the experimental design did as reasonable. And well, if we come back to this pre-session task later, I can comment more on this. It's not usually an inappropriate test that people chose that leads to this problem of the reproducibility crisis. It's not usually the statistics that's at fault. It's not that people assumed something like a normal distribution and it was too far away from that. The problem is usually somewhere else, and so we can pretend the world is okay here. The basic principle for all the tests is you have your observed data, and you take, say, the mean. So you have the average mark that you observed. Then you subtract the expected average mark, assuming your null hypothesis. Now that sounds complicated, but it's actually not that hard because the null hypothesis just assumes that it doesn't affect the kids, how they perform. So you could just take your class and somehow determine in another essay task before that, what's the average mark that the kids achieve in writing essays if they just get some topic. So you can try to get at this. It's often not that hard. And then you have to divide by what's the expected variation you're expecting to see given essentially how large the class is and how variable their marks are. Again, you can do this prior test where you have them write some essay, and then you don't just get an average mark from that for the class, you also get a variation. You get the standard deviation, say, of the marks. Why do we divide by this? Well, we're trying to refute H0, which says these two things should really be the same, right? If H0 is true and we don't have absurd noise, we should get 0 in the numerator. Now, if we don't get 0, that can have different reasons, and noise could be one thing, so we divide by the typical noise. And so the result of this is, if we have a large value coming out of this, called the test statistic, if we have a large value for the test statistic, that means we have a small p-value, because then it's very unlikely that this data is due to random noise, that the difference you see from what you expect is due to random noise. If the difference is big, it's more likely that there's something else going on, some true difference. All right. And here's one example for the student t-test. So the assumption there is that both groups have a normal distribution. You don't know the mean, but you know the standard deviation. It's one of the simplest tests. It's also one where, I don't know, you don't often really know the standard deviation very well. But in our case, you could try by, as I said, running an assay before and measuring it. So here we could take directly the difference in marks as our observed data, and the expected data would be 0 because we assume the means are the same. You can compute that this is the standard deviation of the difference between the two groups. And then, well, that's where the test gets its name from. There's a specific distribution, and you can figure out that the test statistic has this distribution. So you can get the p-value from a lookup table. OK? Have you seen student t-test somewhere? How many have not seen it? How many have seen it? Half. Yeah. There's many more. There's many more assumptions that you can try to get away from for the data. Again, for us, let's ignore that. But on this level of abstraction, the tests are usually all the same. OK, so we have a measure now. We have a means to refute hypotheses by collecting data and seeing how unlikely is it that this arises under the null hypothesis just from random noise, as opposed to being some other true reason. So why is this sometimes problematic? Several points. Now, in principle, this works, right? This is how all our scientific knowledge is collected. And there's some fields that are not really affected by the reproducibility crisis that much. For example, particle physics is doing fairly well because they're stricter in their experimental setup. So it's not like this method in itself is flawed in any way. But there's a few things that are tough. One thing I told you about this gold standard of controlled experiments. Well, it turns out sometimes that's really hard to do. I don't know if you know this story. I learned it's an urban legend. So the forbidden experiment is to raise children and not speak with them at all. And so there's several pseudo-historical accounts of kings who have tried that out, came to various. Basically, the story is always the kids just die. But I think it's very, very shaky evidence, so probably no one has ever done it. It's not clear what would happen. But it's clearly unethical to do this experiment. It would be interesting to find out what happens if you raise children without talking to them at all. Would they develop their own language? So in the past, people thought, oh, maybe they would come up with the true language of God. Maybe they would just invent something on the spot, or maybe they would die. Who knows? I certainly don't think we want to find out the experimental way. And other experiments, it's just very expensive to do them. This is often, I don't know, if you would like to find out, OK, causing cancer is probably on the unethical side as well. But something less controversial, I don't know, does drinking coffee eventually make you more or less healthy. Now, if you want to focus on the eventually, you might want to have health data 10 years into the future. It's tough to recruit people to stay committed to an experiment for 10 years. These are expensive. It's not impossible to do. But often people try to get something cheaper. And there's a way to get at least some information. That's from an observational study. So there, you don't randomly assign people to groups, and you don't have a strict control group. You just collect data and see what happens naturally. So you collect data and see if you ask people, do you drink coffee? And you ask them, are you healthy? I mean, you want to formalize that a bit more. But you can collect such data and try to find patterns, okay? Now, obviously, there's a problem. Suppose everyone who drank coffee also did, well, let's spin this positively. They also did a lot of sports and a lot of other things, and otherwise lead a super healthy life. So that you might find that coffee goes together with super healthy, but it might just not be the coffee that causes it. We've seen something like this with the polar data set for widening participation. We can't really do an experiment with kids saying, we randomly assign you a postcode and see how well you do in higher education, right? It's somewhere between those two. But we have the data that happens to come from how people behave. So it's exactly this kind of thing. It's very, very widely spread. So bad cautionary sign. Observational studies can be helpful, sometimes the only thing we have. But you can only ever observe correlations, things that vary together. You can spot patterns, but you can't easily say this causes that. Strictly speaking, with an observational study, you can never ever do that. There's just it's not possible from the setup of the experiment. There's many examples of this. Like here's one. The typical thing that happens, as for the coffee thing, there's a confounding variable. I should have put that on the slides as a term, but maybe you've probably heard this before. So a confounding variable is something else that is the true cause, but it happens to co-vary with what you study. So a confounding variable would be living healthily. You want to measure how coffee affects health, but there's this third thing that happens to be connected with coffee by chance. And so you can't really separate the two things. There's a fun website where you can randomly, they have lots of data sets, and they just randomly pick out some highly statistically significant correlations between two things. And often it's complete bogus. Well, you can have a look at that if you want. Before I come to the reproducibility crisis, I thought it's useful to bring this back to the essays and the articles that you're reading. Now, this is not something super well vetted. This is something that I'm from reading a bunch of these articles came up with. In well, taxonomy is pitching it high. There are different levels of what things do and then publish as an article in educational venues. It could be just that they've done something and they feel they've learned something, so they want to share that knowledge. It's totally legit. And so people publish such personal experience reports. Again, these terms, I made those up. So that's nothing that is very well agreed upon. I think it hopefully is useful. So have a look at your articles and see whether you can classify them. So this one might just share experience, so you don't make the exact same mistake twice, say. But it's quite limited because you don't know. There's a lot of things that are unclear. It's usually without a control group. So someone did something and it worked well. Awesome. Maybe it would have worked well without him doing anything different from what's the standard, right? A little better can be to ask the participants what they felt. This is often qualitative. So that's another orthogonal axis that I'll come to. So you don't just rely on what the person who ran some activity says, but also what the participants say. it's still fairly weak because you don't really have something to compare it to, right? It worked well compared to what, right? And maybe the participants just were nice in the survey. Observational study, we talked about this before. You can collect data, say in an educational setting, you collect how many schools have access to Apple devices and what's the average marks at GCSE level. Maybe there's an interesting correlation, maybe not. I'm not even sure if it's positive or negative. And even so, it's a correlation. So it's not clear how useful that is, but you can try to learn something like this. I would still say it's this is not necessarily a ranking, but it could be a little more useful than the other two because it's just less local. It's a bit more comprehensive if the data includes more settings. Whereas it could just have been, you know, this was a super selective private school with all well-off kids with private tutors, and your teaching method works well there. That's great, but maybe doesn't help someone teaching in another setting. Hopefully, observational studies are more comprehensive. And of course, the gold standard is some controlled experiment. I've seen this often in advertisement marketing or software. People call it A/B testing. And it's really the same thing. So for a software, you could say a website. You have two designs for a website, and you want to find out what works better, what keeps people, say, the standard metric, what keeps people looking at your page for longer. So you randomly roll out the page in the two designs, depending on when people visit, right? You just flip a coin, but you record what they do. That's a controlled experiment in the sense that you randomly assigned them to one of the two groups. And you could have a control group if you want, if you have a status quo page. So that's just a different name for it. Okay, then I don't want to say that, okay, so you can have either qualitative results or quantitative metrics. I don't think one is strictly better than the other for the following reason. So qualitative experiences, the weakness, of course, is sometimes not clear. It worked well, but is that enough better than something else to bother with the effort? It's hard to judge based on that. Quantitative metrics can have the problem that you measure one thing and it's just a surrogate of the real target. So the trick there is to find a good metric that reflects really what you want to see. In that sense, we often have test scores, which is all right because a lot in life depends on test scores. So if you want, you could say that's the real thing we care about. It's not really the real thing we care about though, right? We would maybe focus on the skills and mindsets or things like that. Or maybe a different metric could be income. Universities sometimes do that, right? They show if you go through our studies with some percentage, with some probability, you make so and so much money after 5 years or so. Whatever you pick as the metric, it shifts the picture. So that's another danger. So people often try to mix these two a bit. So have a look at the essay topics that you picked out and the articles you found, and try to see what they do. Again, I'm not saying that one is not useful or the other is the only thing to go for, but if you put a weight on the evidence, how well does this support some argument you're making? It's useful to keep in mind that some things are inherently limited, or limited in scope. Questions so far? So last bit was this video. Let's switch to the Slido answers. It was a bit more open, I think. Does that work? Yep. Okay, what's the p-value? Talked about this, but it was 20 minutes ago. That's not wrong. It's a measure of statistical significance. I haven't actually talked about statistical significance yet, right? Yeah, significance. That's my definition. How likely is the data, assuming the null hypothesis? Good. specifically, the p-value is not, that will be on the slide as well, is not the probability of the hypothesis you're trying to prove, H1. That's not the same thing, unfortunately. And the second bit is, what can we try to do to improve the reproducibility criteria? Maybe I should summarize that first. So what the video, so okay, the Veritasium videos are often more neutral in the video, whereas the title and the cover, the screen is always a bit clickbaity in itself. So he points out that there are some false positives that you inherently expect from the scientific method. That's kind of inevitable just because we have noisy data and random noise. But we see a few of these results too much to be really happy with. And there's a number of reasons. Is incentives on the science side. A bit more subtle is this publication bias. It's just not as exciting to publish that you did something and it didn't work. There's also problems with the statistical significance of how sure are you it didn't work because of it's actually wrong? Or could you just not show that it is true with your method? The latter is the only thing you can really say. It would be interesting if you could say, oh, I had this hypothesis, it turned out it's not true, and now I know it's not true. But your statement is just, I tried to prove this hypothesis and I failed. That's just a harder sell. Specifically in fields like psychology, people joke that it's the psychology of undergraduate psychology students, because that's the easiest to recruit group for experiments. Yeah, sometimes you have influence like big companies funding research, and then it's not clear how independent it can be. So you had some ideas what you could do. Focus to reproduce research, even if we already know the outcome. It's a good thing. I think everyone agrees we want to do that. It's one of these, everyone likes change, but not to change. Yeah, hopefully you don't do that. We'll talk about the p-value hacking. Yeah, replication studies. Repeat the whole thing several times. That's the best attack we have. Yep. And maybe accept that there's value in just repeating something or disproving a certain way to prove something. The fail doesn't need to be your personal fail. It could be, this is not the way to prove it, whether or not it's true. Okay. I want to comment on this statistical significance bit. Did I skip this on the slide, or was this only at the very beginning? Let me go back to where it was defined here. So yeah, I hadn't introduced p-value at the time, but now you know what it is. It's the likelihood of the data assuming the null hypothesis. And so what is statistically significant? Well, that depends on your field. In psychology and other humanities, often people defined an effect is statistically significant if it has a p-value of 5% or better or smaller. Right? So if the probability that the data you get, the likelihood of the data is at most 5%, assuming the null hypothesis, then you're happy to accept the counter hypothesis. And that's what the video picked up. 5%, well, that's 1 in 20, right? So 1 in 20, we expect to produce a false positive, a statement that I have proven the hypothesis, but it really was just random noise. And if you go to something smaller, like particle physics, I think is even squeezing more zeros in there by collecting more data, you can decrease that likelihood. So statistical significance is often seen as a binary thing. That's what I had on the slide down there. So people report various effects, and then they say, yeah, here the difference between the groups was statistically significant, and here it was not. And that's maybe unfortunate for two reasons. First of all, we have these false positives, and so the yes or no is not really useful. At least they should always report the p-values, which is what people mostly do, but still the interpretation then relies on this binary thing. And the second problem is you can have a highly statistically significant difference between your two control groups, the assay marks, but the difference is 0.001 marks. So it can be highly significant, but super small in absolute value. And it's very easy for people to confuse the two things because common parlance significance is just important without much more clarification. Okay, that's a big no-no. If you do a study, you have to say what you did in all details so that people can check if you made methodological mistakes. Okay, and to hammer down this one last time, the p-value is the likelihood, assuming the null hypothesis. It's not the likelihood that the null hypothesis is true. That's the other way around, right? You can't really talk about this in these terms. So you can't say if your p-value comes out at 4% that, okay, it's only 4% likely that I'm wrong. It's not quite how it works. Yeah. I think that's all I wanted to say. Have a look at your articles and try to look at them through this lens. Just be skeptical. I mean, appreciate what people share with you, but be skeptical to how much that means for your claims. How much can you rely on their statements? Look at the evidence. Don't look at what the summary sentence says.